we have now got pi 1 using Buckingham's pi theorem. We can also do the same and obtain an expression for pi 2. So what we had said before is that pi 2 is equals to, we have the same repeating variable, rho, omega, and d, and then we have another variable apart from the repeating variable. So in this case, we'll have pi 2 being equals to rho power d, omega power e, and d power f. And then the non-repeating variables, we take gh. Having done that, we'll get the dimensions for pi 2 is equals to, the dimensions for rho is m l power -3, and we raise it to power d. The dimensions for the rotational speed is t power -1, and we raise it to power e. The dimensions for d is a length, and we raise it to power f. Then the dimensions for gh is l squared t power -2. So this is what we have on the left hand side, and it should be equals to the dimensions m null, l null, and t null on the right hand side. Similarly, we do for m. We consider the indices on the left hand side. So on the left hand side we have d for m, and we shall be able to say that for m we have d is equals to 0. For t, we look at t on the left hand side, and we find that for t is -1 e there, then we have -2 there, and we'll be able to say an expression for t, that t we have -2 minus e is equals to 0, which gives us e is equals to -2. Then we consider the case for the length, and for the length on the left hand side we have -3d there, we have l there, and we have l there also -2. So in that case we'll say that 2 minus 3d plus f will be equals to 0. So d is 0, so we'll be able to get our expression for f as being equals to -2. So once you have done that, we get our pi 2 is equals to gh over omega squared d squared. This is called usually the head coefficient. The head coefficient we can simply analyze and get an expression for pi 3. You recall that for pi 3 we again have our repeating variables rho, omega, and d. So rho power g, h, and I, and the other variable we'll have as p. So here again we consider the dimensions of pi 3, and that will be equals to, for the mass it will be m l power -3 power g, omega is t -1 power h, and d is l power I. Then for our p we will have m l squared t power -3. Here again we analyze for each of our basic primary dimensions. So for m we'll have m there, g, and we also have m there, which is at power 1. So for m we'll say that 1 plus g is equals to 0, so g is equals to -1. For t, we'll when we look at t, we get that t we have -h there, and we have -3 there. So for t we have -3 minus h is equals to 0, from which we have h is equals to -3. Then for L, you can see that for L we have -3g here, we have that one there, and we have that one there. So for L, we can see that 2 minus 3g plus 1 is equals to 0. So when we analyze this, we'll see that pi 3 will be equals to p over rho omega cubed d power 5. So this is usually called the power coefficient. So we call it pi for the power. The next pi number, pi term, pi 4, will also use the same repeating variables rho, omega, and d. And the other non-repeating variable is mu. So that was I, then this one power j, k, and l. So we again get the dimensions for pi 4, and for the dimensions we have m, l power negative 3 power I, then t minus 1 power k, and l power l, and then for mu we have m, l minus 1, t minus 1. So again, we analyze for m, and for m we have I there, and we have 1 there. So for m, we'll be able to say that 1 minus this, that's actually j. 1 minus j is equals to 0. 1 plus j is equals to 0. And j is equals to minus 1. For t, we can see t there, and we can also see minus 1 there for t. So for t, we can say minus 1 plus k is equals to 0. So k is equals to 1. For l, we have l is minus 3i there, then we have that l there, and we have another l there. So for l, we'll be able to say minus 1 plus 3i plus 1 is equals to 0. So the expression for pi 4 will get to be equals to mu over rho omega d squared. If you look at this, it's actually the reciprocal of the Reynolds number. So the pi 4 actually refers to the Reynolds number. So we can now write the functional relationship. So we can say that f is equals to a function of the head coefficient, which we said is q over omega d cubed. It's a function of gh over omega squared d squared. It's also a function of the, so that's the head coefficient, and it's also a function of the power coefficient p over rho omega cubed d power 5. And it's also a function of the Reynolds number rho over mu over rho omega d squared. So these terms are, okay, this we have said this is the Reynolds number, and these terms are usually called the affinity laws. Which describe the behavior of the turbo machine. So there's a physical significance of these dimensionless groups, and we can explore them further. So that if we say, for example, that for the, let's consider first of all the flow coefficient. So if pi q is, we have said is equals to q over omega d squared, we can see that this is proportional. Omega is the angular velocity, so it's proportional to, or if we can remove one dimension of length here and put it here, it will be omega r. So this is proportional to q over omega r d squared. This was d cubed, and this is also, so this one would be u. So this is proportional to q over u d squared, which is proportional to q over ua, since this is a dimension of area. And this is proportional to the velocity over u. So if we say that pi q is constant, this means that the ratio Vm over U is also constant in the two different operating conditions. Similarly, we can also consider the head coefficient pi h, and we know that pi h is gh over omega squared d squared. So we can take this to be proportional. If you look at this omega and the length dimension, we can say it's proportional to gh over omega r squared. Omega squared r squared, that is proportional to gh over the blade velocity u squared, that is proportional to u v over u squared, and that is proportional to v over u. So here again, you can conclude that if the head coefficient is constant for some given operating conditions, then the ratio v theta over u will be also constant for similar operating conditions. We can also manipulate the non-dimensional terms, and we know that when we can combine non-dimensional terms and they will still remain non-dimensional. So let's consider a case for the pump, and we consider the head coefficient, the flow coefficient pi q, and the head coefficient pi h. So if we take a ratio of this to the power coefficient, this should give us some form of efficiency, which we can call the efficiency based on the pi terms for the pump. So if we put it that way, then we'll be able to see that the head coefficient is q over omega d cubed. The flow coefficient, the head coefficient is equals to gh over omega squared d squared, and the power coefficient is equivalent to p over rho omega squared d power 5. So if we simplify this, we cancel out the like terms and so on, we'll find that this gives us rho gqh over p, and this is the power. So this is actually an expression for the efficiency for a pump. And similarly for a turbine, if we look at the efficiency in terms of pi for a turbine, then we can consider that this is a ratio of the power that is produced to the head and the flow coefficient that is contained within the fluid. So you can say it's pi for the power over the flow coefficient and the head coefficient. So if we again put in the terms that we have already got, the power coefficient is rho over omega squared d power 5, and the flow coefficient is q over omega d cubed. The head coefficient is gh over omega squared d squared. So again, if we simplify this, we'll get an expression that the power produced over rho g qh, and this actually gives us the efficiency for the turbine. So from this we can conclude that when the flow coefficient, the power coefficient are the same at two different operating conditions of a geometrically similar machine, then the efficiency of these two machines are the same at these particular operating conditions.